In this video, we are going to look at activity 8b, which is on percent yield. And the first question says, a reaction that is supposed to produce 25.9 grams of NaCl only produces 18.6 grams when performed in the lab. What is the percent yield for the reaction? So whenever we're doing one of these problems, we need to figure out what we have in the problem. So we know that percent yield is equal to the actual yield divided by the theoretical yield. And then to get it into a percentage format, we multiply by 100. So we need to figure out which one of these values is the actual yield and which is the theoretical yield. So it says the reaction is supposed to produce 28.9 grams. So this is what it theoretically would produce. That's our theoretical yield. And then it only produced 18.6 grams. So this is our actual yield. It's what was actually gotten when they did the experiment in the lab. So all we need to do is do actual divided by theoretical. So 18.6 grams divided by 25.9 grams and then times 100. Notice that the grams will cancel out and we'll just be left with a percentage at the end. So in our calculator, 18.6 divided by 25.9, that gives us 0.718. So if we multiply that by 100, we get 71.81%. But when we're reporting percent yield, we only report it to a whole number percentage. So we're going to round this to just a whole number. So this 1 is going to round up to 2, so this will be a 72% yield. So there's our percent yield. And then the second question, the new chemist calculates the theoretical yield of the reaction to be 80.91 grams. So that's easy. This is the theoretical yield over here. So theoretical is 80.91 grams. When he completes, says competes, but it should be completes the reaction, he records that he obtained 67.51 grams of product. So this is our actual yield. What was the percent yield of his reaction? So we know we need to do actual divided by theoretical, so that's going to be 67.51 grams divided by 80.91 grams times 100 to get us to a percentage. So in our calculator, 67.51 divided by 80.91 times 100 is going to get us 83.438. But we know we're going to round this to a whole number, so it's just going to be 83% yield. So percent yield is just a way of scientists showing how successful a reaction was. So basically how well the reaction went. We can calculate out how much of something we're supposed to get, but then when we do a reaction in the lab, generally speaking, we don't get as much as we're theoretically supposed to. And this can be for a variety of reasons. Maybe some of the reactant got dropped out of your beaker or what you're mixing the reactants in. Perhaps the reaction didn't take place to its final state. It didn't go to completion, and so we got less product than we were expecting. Maybe there were some impurities in our sample, meaning things that are in there that weren't supposed to be, and so it resulted in us not getting the complete amount of our product. There are lots of things that can go wrong, and so percent yield is a way of saying how successful our reaction is. So the first problem we looked at, it gave us both the actual yield and it gave us the theoretical yield. But not all problems will give you the theoretical yield. Sometimes you need to calculate it using stoichiometry. So let's look at this problem. It says when 5 grams of potassium chlorate is heated, it decomposes into potassium chloride and oxygen gas. What is the percent yield if 1.78 grams of oxygen are produced? So we first need to look at the problem and figure out what we are given, what we desire to have, and we need to write down our units and our substances that we're given. So we are given 5.00 grams of potassium chlorate. So I'm going to go ahead and figure out the formula for potassium chlorate. We'll do this up here. Potassium has a +1 charge, and the chloride ion ClO3 has a -1 charge. So when we crisscross, we get KClO3. So 5 grams of KClO3. But we don't want to know how much KClO3 there is, really. We want to know what is the percent yield if 1.78 grams of oxygen are produced. So this is the actual yield. So we're given the actual yield, how much was really produced for oxygen. And we know that's going to be O2 because oxygen's diatomic. So the actual yield of O2 is 1.78 grams of O2. So to figure out our percent yield, we need both the actual yield and the theoretical yield. So before we can find our percent yield, we eventually want to know percent yield, we need to find our theoretical yield of O2. So we need to know our theoretical yield of O2, and then we can figure out what our percent yield is. So we need to take this starting value, this amount of KClO3, and figure out how much O2 could be produced if we start with 5 grams of KClO3. So this is just a stoichiometry problem, and you can rewrite the problem if that helps you. So I'm going to write it up here. How much, or how many grams of O2 can be produced from 5.00 grams of KClO3. So that way it makes it a little easier, it looks more familiar, more like the stoichiometry problems we're used to. So we have our given value, 5 grams KClO3, and we want to know how many grams of O2 can be produced. So if this helps you, just rewrite yourself a problem, a stoichiometry problem to do. So now we need to start, just like we start any stoichiometry problem, we're going to write the correct chemical equation and balance it. So we have potassium chlorate decomposing. So we already figured out that potassium chloride is KClO3, and it's decomposing, so that's going to be the only reactant. It decomposes into potassium chloride, so potassium is +1, chlorine is -1, so it's going to be KCl. So KCl is one of our products, and oxygen gas, and O2. So now we need to balance our chemical equation. So we have an odd number of oxygens, so we're going to go ahead and put a 2 there to make it even, and that means we need to put 2 in front of KCl and a 3 in front of O2. So now we have a balanced chemical equation, so now we can determine our theoretical yield. Sometimes this is also called our stoichiometric yield. So theoretical or stoichiometric yield. So if we do our stoichiometry problem, how much oxygen will be produced? So we're going to start with 5.00 grams of KClO3. And this is a gram to gram conversion, so it's going to require 3 steps. 1, 2, 3 steps to get our theoretical yield. Our first step is going to take grams of KClO3 and convert to moles of KClO3. Our next step is going to be our mole to mole conversion, moles of KClO3 to moles of O2. And then our final step will take moles of O2 and get it to grams of O2. So to do this, we need to find ourselves some molar masses. So you should know how to do this by now. So I'm just going to write in the molar masses for you here. So to find the mass of 1 mole of KClO3, we add the mass of potassium, the mass of chlorine, and the mass of 3 oxygens together, which gives us 122.55 grams per 1 mole. Then for oxygen, we have diatomic oxygen. So the mass of 1 oxygen is 16, so if we multiply that by 2, we get 32 grams per 1 mole. So now all we have left is to fill in our mole to mole conversion, our mole ratio. So there's 3 moles of O2 in our equation, and there's 2 moles of KClO3 in our equation. So it's a 3 to 2 mole ratio. So now we just need to plug this in our calculator. We have 5 times 3 times 32 on top, and then divided by 122.55 times 2. on the bottom. And that gives us a stoichiometric or a theoretical yield of 1.95838. And so now, we know that this is a reasonable amount because it's more than our actual yield. Theoretical yield should really always be more than what we actually get when we do the chemical reaction. Our actual yield is pretty much always less, and if our actual yield is more than we can theoretically produce, then we know that we must have some contamination. Something else must have gotten in our reaction, or maybe we just have water left or something that makes it heavier. But our actual yield should be less than our theoretical yield. So let's go ahead and cancel our units. Moles of KClO3, moles of O2, we're left with grams of O2, which makes sense. And so now we just need to do actual divided by theoretical. So actual is 1.78 grams of O2 divided by our theoretical yield of 1.95838 grams of O2. And since this is an intermediate value, I like to hold on to a bunch of decimal places, at least hold on to the number of decimal places that you have in your actual yield. So 1.78 divided by my previous answer, that gives us, and times 100, it's going to give us 90.89%, and we're going to round this to a whole percentage. That's going to be a 91% yield. So this may seem like a lot of work, but really it's the same, mostly the same kind of problem we've been doing. It's a stoichiometry problem, just with one additional step, that we have to calculate our percent yield at the end. Our next problem says slacked lime, which is calcium hydroxide, is produced when water reacts with quicklime, which is calcium oxide. If you start with 2,400 grams of calcium oxide and add excess water and produce 2,060 grams of calcium hydroxide, what is the percent yield of the reaction? Wow, so that is a lot of information. So let's start by figuring out what information we have in the problem. So we're starting with 2,400 grams of calcium oxide. So this is what we are given for our stoichiometry problem. And then we produce 2,060 grams of calcium hydroxide. So this is our actual yield, the amount that we really did produce. So our actual yield. And we know to find the percent yield, which is what the problem is really asking for in the end, we're first going to have to calculate the theoretical yield. So first, calculate theoretical yield. So that's our step 1, and then step 2 will be to calculate percent yield. So we have to first figure out the theoretical yield and then find the percent yield. So to figure out the theoretical yield, we need a balanced chemical equation because we have to do some stoichiometry. So it says the CaOH2 is produced. So that's going to be our product. When water, so that's one of our reactants, H2O, but I'm going to write it HOH. When water reacts with calcium oxide plus CaO. So when water reacts with calcium oxide, it produces the CaOH2, this slacked lime. CaOH2. Okay, so we have a chemical equation. We need to balance our equation. So I notice that there are 2 hydrogens and 2 oxygens on the reactant side, and there are 2 oxygens and 2 hydrogens on the product side. So that actually worked out nicely. Let's see if calcium's balanced. So there's 1 calcium on each side. So everything's actually already balanced. So that worked out really well. So our equation's balanced, so now we just need to do some stoichiometry. So we are starting with 2,400 grams of calcium oxide, and we want to figure out how much calcium hydroxide comes from that. So we're going to do 2,400 grams of CaO as our starting value, and then we want to get to grams of calcium hydroxide, CaOH2. So that's a gram to gram conversion, so we need 3 conversion factors, 2 and 3. And we should have our answer. Our first conversion factor is going to take grams of calcium oxide to moles of calcium oxide. Then our second conversion factor will be our mole-to-mole ratio, moles of calcium oxide to moles of CaOH2. And then our last conversion factor will take our moles of CaOH2 and convert to grams of CaOH2. Whoops, I did that wrong. OH2. The parentheses should not be there. The 2 should be outside the parentheses. So, we know our mole-to-mole ratio is going to be 1 to 1 because all of our coefficients wound up being 1. So 1 to 1 mole ratio. And now we just need to figure out how many grams are in 1 mole of calcium oxide and how many grams are in 1 mole of calcium hydroxide. So to do that, we're going to use our periodic table and add up the molar masses of each of the elements that make up our compound. So calcium plus oxygen, the molar mass is 56 grams per 1 mole. And then calcium hydroxide, when you add up 1 calcium, 2 oxygens, and 2 hydrogens, it gives us 74 grams per 1 mole. So now we just need to type this into our calculator. We have 2400 times 1 times 1 times 74, and then divided by 56. So we got a theoretical yield of 3171.428. And our given value, our actual yield, is 2060. So I'm going to get rid of these decimal places and just use this whole number here to write it next. So now we just need to find our percent yield by doing actual yield, which is 2060 grams of CaOH2 divided by our theoretical yield of 3171 grams of CaOH2. And then we'll multiply by 100 to convert it into a percent. So let's do this. 2060 divided by my previous answer gives me times 100 is 64.955%, but we know we're going to round to a whole number, so it's going to be approximately a 65% yield. And that is our final answer for this problem. Our next problem says some underwater welding is done via a thermite reaction in which rust or iron 3 oxide reacts with aluminum to produce iron and aluminum oxide. In one such reaction, 258 grams of aluminum and excess rust produced this much iron. So this right here, this thing that was produced, this is our actual yield. And this 258 grams of aluminum, this is our given value. So we need to write a chemical equation so we can do some stoichiometry with this given value, figure out how much iron should have been produced theoretically, and then take our actual yield and divide it by our theoretical yield. So we need a chemical equation. So let's see. Rust or iron 3 oxide reacts with aluminum. So we have aluminum reacting with iron 3 oxide, so that's Fe with the +3 charge, and oxygen -2, so that gives us Fe2O3. So those two things react together to produce iron, so Fe, and aluminum oxide. Al with the +3 charge, oxygen with the -2 charge gives us Al2O3. So now we need to balance our equation. We have 3 oxygens, that worked out nicely. So we have 2 irons, we need to put a 2 here, 2 aluminum, so we need to put a 2 over here. And the rest I'll fill in with 1, so we know our equation is balanced. Now let's do some stoichiometry. We have 258 grams of aluminum to start with. 258 grams of aluminum. And then we're doing a gram to gram conversion, so that's going to need 1, 2, 3 conversion factors. Our first conversion factor will take grams of aluminum and convert to moles of aluminum. Our second one takes moles of aluminum and takes us to moles of our new substance, which is iron, Fe. And then our final conversion factor will take moles of iron and convert to grams of iron. Okay, So our mole-to-mole ratio comes from our equation, so 2 iron and 2 aluminum. And then our mole to gram conversion comes through the periodic table. So 1 mole of aluminum, if we look at the periodic table, it's about 27 grams of aluminum. And 1 mole of iron, if we look at the periodic table, is 55.85 approximately grams of iron. So now let's type this into our, well, let's cancel some units. Grams of aluminum cancels, moles of aluminum cancels, and moles of iron also cancels. And then these 2's, we have 1 2 on top of another 2, so those can also cancel out. So all we have is a few numbers left to put in our calculator. 258 times 55.85, and then divided by 27. So I got 533.678, if I round that, grams of Fe as my theoretical yield. So this is our theoretical yield. So now I need to do actual yield divided by theoretical yield. 464 grams of Fe, and my theoretical yield is larger than my actual yield, so that makes sense. Divided by 533.678 grams of Fe. Then we'll multiply by 100 to get it to a percentage. So let's see, we have 464 divided by 533.678. That gives us about an 86.94% yield, and we are going to round that to an 87% yield. This last problem here goes ahead and gives us the chemical equation written out, and all we have to do is balance the chemical equation. And there's no line here, so I'm going to actually put a line there to remind us that we need to balance everything. So let's look at this equation and go ahead and get it balanced. So I notice I have nitrogen in 3 places in this equation. So I'm going to leave nitrogen to be balanced last. So I'm going to start with either hydrogen or oxygen. So hydrogen, I notice I have 4 over here and only 2 over here. So I'm going to put a 2 to double this and correct hydrogen. So now I have 4 hydrogens and 4 hydrogens, but now I need to correct for oxygen. And there are 4 oxygens, and I only have 2, so I actually need to change this coefficient again. This time I make it a 4 to correct for oxygen. So by doing that, I threw off my hydrogen again, so 2 times 4 is 8 hydrogens, so I need to come over here and put a coefficient of 2 to make 8 hydrogens on our reactant side. So now let's check again to make sure nitrogen and hydrogen are both balanced. So we have, well actually let's do nitrogen at the end. We have 8 hydrogens, okay, and we have 8 hydrogens over here, and we have 4 oxygens and 4 oxygens. So now let's take a look at nitrogen. So we have 2 times 2, we have 4 nitrogens here, and we have 2 nitrogens here. So then we need to have a total of 6. So we need 6 on our product side, so we can put a 3 here. 2 times 3 gives us 6 nitrogens. So now this equation is correctly balanced. It's a little bit of a tricky one because you had to change a coefficient more than once. So now I'll fill in a 1 here, and we have a correctly balanced equation. So let's continue to look at our problem. It says if you begin with 400 grams of N2H4 and excess N2O4, so we have tons of extra of this, how many liters of water vapor will theoretically be produced? If the reaction yields 345 liters of water vapor, what is the percent yield of the reaction? So ultimately, what we want to find is percent yield. So we want to do actual divided by theoretical. And it already gives us the actual yield. It tells us that it yields 345 liters. So we just need to find the theoretical yield to be able to solve for the percent yield. And it's also asking us to find how much water vapor will theoretically be produced. So it wants the theoretical yield of water vapor, which is just what we need here. So we need to find both things. This is just a percent yield problem. It just states the problem slightly differently. So we're starting with 400 grams of N2H4. And take note of the fact that we're looking for liters of water vapor and that our actual yield is in liters of water vapor as well. So this is a gram to liter conversion. So we still need 3 conversion factors, but in the end we're going to get it into liters of water vapor. So first we're going to convert grams of N2H4 into moles of N2H4. Next we're going to take our moles of N2H4 and convert it into moles of water vapor of H2O. And then finally we'll take our moles of H2O and convert to liters of H2O. So for our mole-to-mole ratio, we just look at our problem, 4 moles of H2O and 2 moles of N2H4, a 4:2 ratio. Then we need to add up the molar mass of N2H4, so 1 mole of N2H4, if we add up 2 nitrogens and 4 hydrogens, that gives us 32 grams per 1 mole. And then we know that the number of liters in a mole is always the same. The number of liters of gas in 1 mole of gas is always 22.4 liters. So now we can solve this problem. We can go ahead and cancel some units, grams of N2H4, moles of N2H4, moles of H2O, and then last this 4 can cross out and become a 2 and cancel this 2 at the bottom. And then we can also reduce this 2 can cancel to a 1, and this can be divided by 2, so this would be 16. So we can do some of those cancellations in our head, and now we just need to put the rest in our calculator. 400 times 1 times 1 times 22.4, and then divided by 16 times 1 times 1. So divided by 16, that gives us 560 liters of H2O. So now we just need to find our percent yield by doing actual 345 liters of H2O divided by our theoretical yield 560 liters of H2O. Times 100 to give us our percentage. So 345 divided by 560, that gives us 61.607%, which we can round to a whole number to be 62% yield.